Hey online folks, here's the problem. Some of you did not get your kit still. So what I'm doing is doing lab number 3, graphing motion, and I'm going to take the data for you. I'm going to actually show you what I'm going to do, and then I'll just either shoot you an email with the data, or maybe we'll take some pictures of where the meter stick is with respect to where the dots are, so you can take data right off the pictures. So right over here I got the school's version of the ticker tape timer. Now it's a little different than what we used and described in the lab kit that you would have gotten. This is 40 hertz for the frequency. That means it's 1/40th of a second instead of what you were trying to get for your lab. So your lab is not going to do part 1 where you find the period of the ticker tape timer. I'm just going to give it to you. It's 1/40th of a second because the frequency is 40 hertz. So here goes. All we're going to do is turn the ticker tape timer on and make little dots show up. Hopefully your hypothesis described exactly what the dots are going to look like for constant motion. So I'm going to turn this on to 40 times a second. Nope, that's 10. 40 times a second. And let it rip. Alright, now we'll take the data. And okay, so now we do the third part. First part we're skipping. Second part was uniform motion, or UM. Now it's uniform accelerated motion. We're going to let gravity pull this mass down, but it's connected to the ticker tape timer. So now that when I go like this, watch my feet.
Too fast.
Got myself acceleration. Okay folks, so now we have the tape next to a meter stick, and if you recall, the period is 1/40th of a second, and this one I went every 4th dot. Now think about it. If every 4th dot, that's right there, it's 1/40th of a second, 2/40th of a second, 3/44, 4/40ths, or 1/10. So I numbered that dot number 1. That's 1/10 of a second later after that. So here's right there 1. Okay, so at 1/10th of a second, where is it? How many centimeters away? You should be able to read at least to the millimeter after 2/10ths. Where was the cart? 3/10ths. Where was the cart? 4/10ths. See, I numbered it number 4 because the denominator will always be 10. Pretty smart, huh? Look where the dot is and look and see if you can measure where that is. Number 5, 5/10ths of a second, or a half a second later, where is it? 6/10ths, 7/10ths, 8/10ths. Read this, you might have to pause the video. 9/10ths, 10/10ths. Now you're still going to leave it as tenths. It's easier to graph if you just leave the denominator as tenths of a second. 11/10ths. Where is it? How far did it go after 12/10ths? Write this data down. 13/10ths of a second. What distance did it travel? This is all a table of time and distance traveled. Distance depends on the time, so the time's on the x-axis. And 16/10ths, how far away is it? 17/10ths, 18/10ths, 19/10ths, looks like 46 point something. Read that. And last one, 20/10ths. After 2 seconds, where did it go? Where was it? Now you can graph time on the x-axis, distance on the y-axis, because it depends on the time, and be able to form a graph, and the slope of the line should give you how fast the cart was going. Okay, now here's the tape for the falling mass. The falling mass is called uniform accelerated motion. This is going to generate graph number 2, which hopefully will look like a parabola because this is accelerating and you hypothesized correctly. And then you should be able to graph with the Ortenzi cheating method from another table called velocity in time. So here we go. This time we went every other dot. Write that down quick. Every other dot. We skipped every other dot. So that means going from 0 to 1 is 2/40ths of a second, or 1/20th of a second. So that number 1 there, how long did it take for the mass to move that far? 1/20th of a second. We went every other dot, and the period is 1/40th, so that's 2/40ths or 1/20th. So now the denominator is going to be 20ths. So I put the first dot right on the 0, and then number 1, 1/20th of a second later, where is it? See if you can determine where it is after 1/20th of a second. How about number 2? Where is that dot? Try to read to at least a millimeter, plus or minus probably a millimeter for number 2. 3/20ths of a second later, look how far it went. Did your hypothesis match what I'm looking at here with these dots? Way over here for 4/20ths of a second. Look how far it went. Look where the dot is, and look what part of the meter stick lines up with that. 5/20ths of a second later, it went all the way over here. 6/20ths of a second. It's really picking up some distance. 7/20ths of a second later, it's almost 60 centimeters away. Way over here for 8/20ths of a second. See if you can read where that dot is in comparison to the meter stick, plus or minus. And then 9/20ths of a second, it is already at 90 something. Read that. And since I couldn't find my 2-meter stick, I did a really lame thing here and went to the last dot, which is 10, and see if you can kind of get a really bad data point on that. Use it with a grain of salt on that one. Okay, so that's the data for the falling mass. That would be part 3 of your lab. Okay folks, so that's hopefully the video will give you the data for lab number 3. Let me just remind you that you were looking at 4 different graphs. First graph, uniform motion, distance over time, should give you a nice straight line for a slope. Draw a best fit line somehow on your own without Bill Gates helping you. And then graph number 2 is uniform accelerated motion. Again, distance versus time, but this time you should get a parabola, so you do a best fit curve. And then I want you to do a tangent line at 3/40ths of a second, actually 3/20ths of a second for that one. 3/20ths of a second, you're going to do a tangent line. The directions will say 3/30ths, but that's because we were using a different ticker tape timer on the original video. Okay, remember, this ticker tape timer has a period of 1/40th of a second. We went every other dot on the falling body one, so that is 1/20th, 2/20ths, 3/20ths, because we went every other dot. You're using the cheating method, so actually you're going from the dot before to the dot after to find the instantaneous for graph number 3. So graph number 3, I'm looking for velocity versus time, and you're using my cheating method in order to get those instantaneous velocities. They're really mini average velocities, so you don't have to do 10 tangent lines. You only have to do 1 tangent line on the previous graph at 3/20ths. Okay? The last graph, the 4th graph, is velocity versus time, not distance versus time, velocity versus time for the ball drop video. So I want you to do that 4th graph using the ball drop. Be careful, because that period of a video camera is 1/30th of a second for every frame, which means be careful what you're going to have as your time intervals for finding the cheating method in order to get the velocities. Okay? So that should be it. You should have all the data you need now to do this even without a kit. Thanks.